Hey, my name is Zach Lassiter, and I'll be discussing a lab I did about finding the mass of a black hole. In this lab, a star was orbiting a black hole of unknown mass. I was given the position data of the star in a CSV file, the time step, and the mass of the star. I then analyzed the star's motion in v idle to find the net force on the star for all points in the dataset. I assumed the net force on the star was solely due to the black hole. I then solved the gravitational force equation for the mass of the black hole and put that into my v idle code. When the code was run, a mass of 1.9902 times 10 to the 31 kilograms was outputted for the black hole. Here we have some equations used in the lab. The first one is the gravitational force equation, which is equal to negative g times mass 1 times mass 2 divided by the distance between the mass 1 and mass 2 squared times the direction vector. The next equation is the momentum principle, which is equal to mass times final velocity equals mass times initial velocity plus F net times delta t. And if you derive all this, you get dp divided by dt equals F net. Here we have F net is broken down into its two components, F net parallel plus F net perpendicular. And since F net is equal to dp dt, we can set dp dt equal to F net parallel plus F net perpendicular. And so dp dt is equal to dp over dt times the direction vector p plus the speed times the change in the direction divided by the change in time. This one represents parallel because it's a change in speed, and perpendicular is represented by this because it's a change in direction. This equation right here, we just solved it for the perpendicular, the F net perpendicular, because that is later used in our code. Let's go over to the code now. Here we put in the black hole so that it will show up in the module. Here we have the mass of the star is equal to 1.989 times 10 to the 30 kilograms. The initial position of the black hole, which is negative 4 e to the 10 meters in the x. Here delta t is equal to 86,400 seconds, which is the number of seconds in an Earth day. We go down to our first while loop. You can see that we computed the x component of velocity using these two lines of code, and then we computed the y component of velocity using these two lines of code. And to our second while loop, we had to find the initial velocity, and the final velocity, and as well as the final momentum and the initial momentum. This was all used later to find that we could find dp dt is equal to delta p divided by delta t, and F net equals dp dt. And with this, we could calculate dp dt parallel as well as dp dt perpendicular, which is dp dt minus dp dt parallel, which was I showed earlier in the equations for this lab. As we go down, we can see that to calculate the mass of the black hole, I had to set g equal to 6.67 e to the negative 11, and the mass of the black hole is equal to the mag of F net times the mag of the star position minus black hole position squared divided by g times the mass of the star. And here I just printed out T mag of F net parallel, mag of F net perpendicular, as well as the mass of the black hole. Now if we run this module, it is very slow. The yellow arrow represents the F net perpendicular because it's pointing to the star. The F net total is the yellow one because it's the force of gravitation of the black hole pulling the star in. The blue one's the perpendicular, and the black one is the parallel. And the black parallel is going backwards, or is in the opposite direction of the motion because the star is actually slowing down because it's getting farther away from the black hole. And that's going to keep going for a while. So, and as you can see, it's the two values. It's like 1.99 e to the 31, which is what we calculated earlier. Here, what does it mean? In your analysis, you should discuss how F net perpendicular, F net parallel, and F net are different from delta p divided by delta t perpendicular, and then delta p delta t parallel, and the change in momentum divided by change in time. These are different in that F net equals dp is derived from the momentum principle. dp dt is something that can be calculated from the observed position data. However, F net is the force that is causing the observed motion. It is not something that we can measure directly. Therefore, it is different because F net is qualitative, while dp divided by dt is quantitative. And what if? Imagine that the black hole whose mass we found was removed and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? You could not tell a difference between the two because they would both have the same mass. The new black hole is in the same location as the old one, and the motion of the star is the same. This means that the mass of the black holes are the same, and to calculate the mass of the new black hole just by running the code in vidle again. That is all I have for this lab. So thanks for watching. If you liked this video, make sure you liked it and subscribe to my channel for more amazing physics labs like this one.